We're beginning Unit 2 on polynomials, and our first two lessons are on exponents and their properties. There's only two real objectives to this lesson. One is that you can simplify real number expressions that have rational exponents, and the other is that you can simplify algebraic expressions with rational exponents. Before we continue, let's think about what you already know about exponents. Some of you may have had some lessons on them before. So I would like for you to jot down anything you might know about exponents. Maybe you can make an exponent or give an example if that helps. Push pause, and when you're ready to continue, push play again. Okay, either you're ready to begin, you wrote some things down, or you just waited for me to start talking again. Either way, it's okay. So, what do you possibly write down? Well, I see students sometimes write down little number because they kind of remember something about exponents being some kind of little number involved. Or maybe you gave a number and put a little number up in the air like this. Those of you who've had exponents before or worked with just numeric exponents, like the one you see here, you might have done something like this. And then maybe even continue doing this. If you can get to this stage right here, you're doing pretty well, and you're halfway there is part of this lesson today. Regardless of your background with exponents, we'll review some vocabulary. The base. Base is the bottom number. The base is the number that's repeatedly multiplied. The exponent tells us how many times the base should be multiplied by itself. It's a shorthand way of repeated multiplication. So altogether, this is called a power, and a power is just a number that can be expressed using a base and an exponent. So we call it in power form. So a number in power form, to get it in what we like to call standard form, or sometimes just say simplified, you take the base, remember that the bottom numbers are base, times itself as many times as the number of your exponent. So because our base is 2, 2 is the number that you're multiplying. The exponent 3 tells you how many times you are multiplying the 2. We're multiplying by itself 3 times. What I've done here is what is called expanded form. If you do not have use of a calculator, you would have to always take your power form and write it in expanded form in order to solve, unless you have some of your more frequently used powers memorized or exponents memorized. So to solve this, or to simplify it, you'd multiply two numbers at a time and then multiply their answer by the next number. So 2 times 2 is 4, 4 times 2 is 8, and that's how they got the 8. So this number right here is either called standard form. I wrote stand form instead of standard form, sorry. Or you'll just simply see the directions simplify. Sometimes even the word solve, because there's an equal sign. Those of you working with equations before, you know you only solve when you see an equal sign. Simplify just means getting it down to where you have no like terms. If you do have the luxury of using a calculator, solving numeric exponents can be pretty easy. To type it in the calculator, you'll first start with typing the base, the bottom number, into your calculator, whatever number that might be. Now warning, because this will change your answer significantly. If the base is a negative number, you will need to put parentheses around it. you'll need to use a scientific calculator or a graphing calculator in order to solve exponents. Most four-function calculators are unable to solve exponents using this simple button. You'd have to multiply it out, like 3 times 3 times 3. So there is a button to make this a whole lot shorter. First of all, I need to point out the parentheses in a graphing calculator. Those are right here. I've got my other calculator covering up, but there's one right there and one right beside it. They're always side by side to one another, so those are our parenthesis buttons. After you type in your base, then you will type your exponent button. Now, depending on what calculator you're using, the exponent button might look a little differently. In some calculators, like the scientific calculators we have here at the Excel Center, they have a caret. And same with the graphing calculators we have here at the Excel Center, you'll see the caret button. So that is your exponent button. It's like telling you to put that little number up in the air. If you have other styles of scientific calculators, you may see this button here has an X with a little Y up in the air. Again, it's saying you want a little number up in the air. There are other buttons for using or solving exponents that for the most frequently used exponents, like you already know what the exponent is going to be. I would recommend just sticking with using these buttons because it works with any exponent. So after you type in the base and then your exponent button, then you'll type in the exponent and press enter or equal, depending on if your calculator has an enter button or if it uses the equal sign. Pretty easy. So let's practice this. 5 to the second power, well, that means the same thing as 5 times 5. What's 5 times 5? 25. Oops, I wrote 24. 25. Okay, so this is your expanded form, and I simplified it further into our standard form. Focus question 2. You have 3 to the third, which is the same thing as, sorry, this was 5 times 5. It's 25. There we go. 3 to the third is the same thing as 3 times 3 times 3. To solve that, you need to multiply two numbers at a time. 3 times 3 is 9. 9 times 3 is 27. Exponents are a way of coding patterns. Knowing how they behave can make working with using them much simpler. Today, your job is to observe the behaviors and come up with general rules about them. So we're going to do a little discovery learning. So we have some rules with exponents that have variables. When your base is a variable, or just if any time the base, the number that's down below, is the same, when you are multiplying variables with exponents, you will add their exponents if they have the common base. Let me just read that because I just fumbled all over my words on that one. Sorry about that. So products of like bases. Remember, product means to multiply. To multiply powers with the same base, add the exponents, but keep the common base. And they gave you an example. X to the fifth times x to the third. Yes, if they're side by side, that means to multiply. They don't need to put a little dot between them. Or they definitely will not use the times symbol. So you see x to the fifth times x to the third, and you see they combine it. If the bases are the same, then you add the exponents. 5 plus 3 is 8. So x to the fifth times x to the third is the same thing as x to the eighth. When you have quotients of like bases, or whenever you take the division of two numbers that have the same base, you divide, or division of powers of the same base, you would subtract their exponents and keep the common base. For example, x to the fifth over x to the third is the same thing as x 5 minus 3 equals x to the second power. Now be careful on this, and I believe I'm going to say this a little bit later. When you subtract, whichever power is larger, the top power or the bottom power, for example, the x to the fifth is 5 is larger than the 3, then my x to the 2 will stay on top, or is a numerator. Now there's nothing on the bottom of this example. Let me write something down here. But remember, you can think of it as like over 1. You will not need to write the over 1. Later on, this will make sense why I'm emphasizing this. When you're taking a power of a power, and you'll notice this when you see parentheses. If you see an exponent directly outside or next to parentheses, then this means a power of a power. To raise a power to a power, you will keep the base but multiply their exponents. It's like using the distributive property. You take the 3 and you multiply it to the 5 inside of the parentheses. So x 5 times 3, so it would be x to the 15th. And finally, when you see a product to a power, this is also like using your distributive property. When you raise a product to a power, you raise the factor to the power. So you would separate each base and take it each one to the power. Okay, I'm not doing a great job of explaining, but I can show it to you. Here you have x to the 4th times x to the 5th to the power of 3. So that 3 distributes out to and multiplies to each exponent of every term or variable, or every number or variable that's inside of that parentheses. So you have x 4 times 3 is 12, y 5 times 3 is 15. I'm hoping that they'll give you some examples with some numbers here in a minute too. Don't worry, we'll practice these. We're just summarizing all these rules. The 5th rule is quotient to a power. So this is when you have what's a fraction inside of parentheses to a power. In this case, you will need to take the outer power and multiply it to the power of every term, whether it's on the numerator or the denominator, inside of the parentheses. So you see here this 4 that's to the power of this fraction, so you would multiply it to every exponent of every term and variable that's inside of the parentheses. So 3 times 4 is 12, that's how you get x to the 12, and y times 4 is 8, so y to the 8th, and it stays on bottom then. The next rule is the zero exponent rule. Any number at all raised to the 0 power is equal to 1. Any number raised to the 0 power is equal to 1. Same with any variable raised to the 0 power is equal to 1. So in our example, they are sort of combining two of the rules that we just discussed, the power of the product rule and the 0 rule. To see how they get this, well, it didn't matter. This whole amount, when it's anything to the 0 power is equal to 1, I could have written 8 to the 0 power x to the 4 times 0 and used one of our other rules that you just did. But regardless, 8 to the 0 power is equal to 1. 4 times 0 is 0, so that would still be x to the 0 power, and that equals 1, and 1 times 1 is 1. So anywhere you slice it, when you see a 0 power, then you know it's always equal to 1. Finally, our next rule is the negative exponent rule. When you're working with polynomials, we never, ever, ever like to have negative exponents. To change a negative exponent to a positive exponent, you simply move the term to the numerator or the denominator, whichever the opposite of its location. I like how they describe this. They call it switching the floors. So a negative exponent indicates reciprocal. with the exponent and the reciprocal becoming positive. You want to think of the unhappy negative exponents would become happy or positive by having their base or exponent pair switch floors. That's kind of cute. So for example, 8 to the negative 2 power is the same thing as 1 over 8 to the positive 2. We simply moved it to the denominator. And then you can also simplify 8 to the second power as 8 times 8 is 64. So you'd have 1 over 64. Another example you see there is 4 over x to the negative 3. The 4 is positive, so it's going to stay where it's at. But the x has a negative 3 exponent, so we are going to move that variable term up to the numerator, leaving nothing on our denominator, so we do not need to have a line with a 1 under it. This is what I was explaining before. We don't need to have the line with the 1 under it. If there were any other variables on that denominator that were positive, we would not move them. We would leave them on the denominator. Alright, as I promised, we're going to practice these and we are going to discover some patterns here. So let's evaluate these problems here. Here we have the number 2 raised to various exponents. So 2 to the 4th. What is that equal to? Well, 2 times, I'm going to use dots instead of x's here because we're going to have some variables later. So 2 times 2 times 2 times 2. So I have 4 2's that I'm multiplying together. What is that equal to? Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2, I had to think about this, 8 times 2 is 16. So 2 to the 4th is 16. 2 to the 3rd is 2 times 2 times 2. Simplify that, or in other words, they say evaluate. The word evaluate and simplify is just getting it down to one number. So they will use those words interchangeably on the ECA. 2 times 2 is 4. 4 times 2 equals 8. 2 to the second power is 2 times 2. 2 times 2 is 4. 2 to the first power. 2 to the first power is equal to, well, I just have 1 2, so I'm just left with 2. 2 to the 0 power, there's that rule again, is equal to 1. 2 to the negative 1. To take 2 to the negative 1, you'd first need to make that that exponent positive by moving it to your denominator. So 1 over 2 to the positive 1 is equal to 1 over, well, if there's only 1 2 there, it would just be 1/2. 2 to the negative 2 power, you want to remove that negative sign by moving it to the denominator, switching the floors. And then 1 over, well, whatever 2 times 2 is. 1 over 2 over 2 is 1 to the 4th. So do you notice any patterns? Well, as our exponents increase, at least I notice that their numbers are doubling. But as our exponent's decreasing, after it gets past 1, it's just a fraction, but the denominator is doubling. It's just repeating. What do you expect that 2 to the negative 4th is going to equal to? 2 to the negative 4th. Just by looking at this pattern. How about 1 over 16? If 2 to the positive 4 equals 16, then 2 to the negative 4 will be 1 over negative 16. I'm not sure if what I said just now, but I meant to say 1 over positive 16, not negative 16. So on your paper, hopefully you were filling those in. As we're going along, make sure that you do that. Using the information from the previous slide that you've written down, let's complete this table below. If your exponent is 0, for every non-zero number a a to the 0 is equal to 1. So 6 to the 0 equals 1. That means negative 24 to the 0 power equals 1, right? Any number, any variable, or any number to the 0 power is always equal to 1. If you have 7 to the negative third, it's the same thing as 1 over 7 to the positive third. 7 to the third is 343. It'd take you a little while to do that by hand, but you could do it in your calculator, punching your base, your exponent button, your exponent, press equals. 4 to the negative 2 power is the same thing as 1 over 4 to the 2 power. And 4 to the second power is, well, 4 times 4 is 16. We could do that in our head. So looking at the next example, negative 3 to the negative 5th power is the same thing as 1 over negative 3 to the positive 5th power. Notice that our negative 3 stays negative. You don't change the sign of the base, you only change the sign of the exponent. So what's that equal to? If you have a calculator, go ahead and use it. This is important to check to see if you are using your calculator that you are using it correctly with those parentheses. Because notice our base is a negative number. So if you're using your calculator, it must be inside of parentheses. Otherwise, you will not get the correct answer of negative 243. You might have gotten a positive number of 243. So it makes a difference that you put those negative numbers inside of parentheses. Whenever you take a negative number to an odd exponent, you should always get a negative number. If you take a negative number to an even power, you should always get a positive exponent. I'll write that off the side because I'm not sure if that's discussed later on, so you need to add that to your notes. There we go. Any negative number to an even power equals a positive. Any negative number to an odd power should always equal a negative. So let's try this. What's 812 to the 0 power? Hopefully you wrote down 1. 34 to the 0 power? 1. Any number to the 0 power is always equal to 1. What is the simplified form of 4 to the negative third? Well, you would put 1 over 4 to the positive third. Evaluate the 4 to the third power. Well, 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 24, 2, 4, 5, 6, 64. 6 to the negative second power is the same thing as 1 over 6 to the second, which is the same thing as 1 over 6 times 6, which is equal to 1 over 36. 2 to the negative fourth, 1 over 2 to the positive fourth, which is equal to 1 over 2 times 2 times 2 times 2. By the way, 2 to the third and 2 to the fourth become very frequently used exponents, not only in practices that you'll have here with us, but also on the ECA. So you might start memorizing what 2 to the fourth power is eventually. 2 times 2 is 4. 4 times 2 is 8. 8 times 4 is 16. Alright, let's apply the product rule. Here we are multiplying numbers that have the same base. Remember, when you have the same base, you have to add their exponents. So 1 to the first power times 1 to the first power, which is the same thing as just, or not 1 to the, 2 to the first power times 2 to the first power. Remember, you don't normally write the exponent of 1, so it's just the same thing as 2 times 2. What's 2 to the second power then, therefore, is equal to 4. 2 to the second times 2 to the second Well, 2 to the second is like 2 times 2 times 2 times 2. So we had 2 2's here, 2 2's here. You're still multiplying all together. It's the same thing as saying 2 to the 4th, right? We've done this several times. That equals 16. 2 to the first is just 1 2 times, sorry about my dog. Sorry about that. I think she's stopped now. So we have 2 to the first, that's just 1 2 times 2 to the third, so that's 1 2 3 2's. So that's the same thing as, oops, sorry. That's also the same thing as 2 to the fourth. So if you have 2 to the fourth, 1 2 3 4 times 2 to the second, so times times 2 times 2. So how many 2's do you see there? 1 2 3 4 5 6. So it's the same thing as 2 to the 6. Now I'm not going to finish writing these in standard form. We'll just kind of simplify them, putting them together so that it's only one term. So when we simplify an expression, that means getting the power down to one term. Evaluating means getting it down to standard form. Okay. One term. So we have 2 to the third times 2 to the third, so we have 1 2 3 times 1 2 3 2's. So all together, again, that's 2 to the sixth. So what's true about 2 to the second times 2 to the second and 2 to the first times 2 to the third? Don't they both equal 2 to the fourth? So what's the patterns that you see? And what relationship do you see between the exponents in the first column and those in the simplified expression in the third column? Do you see that you just simply add the exponents together? So you can summarize that observation. When factors' bases are the same, factors meaning numbers that you multiply together, are the same, you add their exponents to simplify them. In other words, we can generalize this into using variables to represent the numbers and to represent words. So using the variables m and n for the exponents and a as the base, let's make a rule. When you have any number to one exponent times the same number to, it could be the same exponent or a different exponent, it's always equal to that same number to the power of the two exponents added together. So that's our generalization. This is the multiplication property of exponents with the same bases. Let's see if we can discover any patterns with division. Complete the following table and then answer the questions below that will appear in a minute. So the first one's been done for you. They have the quotient or division of 2 to the 7th power over 2 to the 3rd power. We've expanded our numerator, 2 to the 7th power, so 2 times 2 times 2 times 2 times 2 is 7. And we expanded the denominator, 2 times 3, or not 2 times 3, 2 to the 3rd is 2 times 2 times 2, so 3 times. You can simplify this for every numerator and denominator with the same number always cancels out. So those 2's canceled out. There's only 3 2's on the denominator, so we're still left with 4 2's on our numerator. Our answer is 2 to the 4th. Let's see if you can finish completing the table and then try to generalize this to learn about our division property of exponents with the same bases. Okay, on our next example we have 5 to the 4th, so you write 5 times 5 times 5 times 5 times 5. 5 5s on top, 1 5 on bottom. We can cancel out one of the set of 5s, and we're left with 4 5s on our numerator, so 5 to the 4th. Our next example, we have x's. Now this x is being multiplied by itself 5 times, so how would you write that? X times x times x times x times x. So 5 x's. Over top, how many? Times 2 x's. Can any cancel out, just like we did the numbers before? Yeah, sure. For every x on top and x on bottom, we can cancel out. So we're left with x to the 3rd. So what's our rule we can make about this? Let's use our same variables as before. If we have any number to a power divided by this with the same base to another power, or exponent, it's equal to that same base to the power of the subtraction of the two exponents we started with. So there's our rule. The division property says if you have the bases of two numbers are the same, you subtract their exponents. Alright, let's try some practice problems, and hopefully you'll see some of our warnings that we have when we do these. So think of it, if we have 3 to the 4th, that's 3 times 3 times 3 times 3, let's write them out in expanded form, all over 3 to the, what power is that bottom number as our denominator? I don't see an exponent on it. All numbers and variables do have an exponent. If you don't see it, it is 1. Just like coefficients. So we have 1, 3. One pair of 3's can cancel out, so how many do we have left over? We have 3 3's left over. 3 times 3 times 3. Let's try our second one. 5 to the 6th is 5 times 5 times 5 times 5 times 5. 1, 2, 3, 4, 5. Oop. Forgot one, 6. All over 5 to the 2nd, which is 5 times 5. We have two sets of 5s that can cancel out, and you're left with 4 5s. So 5 to the 4th. Think you got the hang of this so far? Let's try another one. 5 to the 6th again. 5 times 5 times 5 times 5. There's 1, 2, 3, 4, 5, and 6 all over 5 to the 5th. 1, 2, 3, 4, 5. Cancel out. Now would we have to keep on expanding? Do we know this pattern? 5 to the 6th over 5 to this. You just take 6 minus 5 is 1. So 5 to the 1st. What's 5 to the 1st? Just 5. So in all of these so far, we could have just subtract their exponents instead of writing out in an expanded form. Alright, we're going to get a little tricky here then. Let's try subtracting this one. 3 minus 6. What is 3 minus 6? 6 is bigger than 3. 3 minus 6 is another way you could write this. So what's 3 minus 6? Well, it's negative 3, isn't it? Opposite signs you have to subtract. And we never leave an exponent as a negative, so you would have to move it to your denominator. So 1 over 6 to the positive 3. So a shortcut of writing, instead of writing it all in expanded form, we could have, like in this one here, wrote 3 to the 4 minus 1 to get that 3. On question number 2, we could have wrote 5 to the 6 minus 2 to get the 5 to the 4th. Question number 3, that was a 5 to the 6th minus the 5th to get 5 to the 1st. Taking a look at power to a power. Use what you learned about multiplication of exponents, and let's complete each statement in the table. The first one's been started, well, the first few of them has been started for you. 3 to the 6 to the power of 2. So because we're taking 3 to the 6 to the second power, that means you're multiplying 3 to the 6 times 3 to the 6th. And we know that when you multiply two numbers with the same base, you just add their exponents, don't you? And well, also remember in mathematics, the repetition of addition is the same thing as multiplication. So if we have 2 6's, it's the same thing as 6 times 2. Well, 6 times 2 is 12. So 3 to the 6th power to the second power is the same thing as 3 to the 12th. Let's take a look at the next one. We have 5 to the 4th that's to the power of 3. So we take 5 to the 4th times 5 to the 4th times 5 to the 4th, so 3 times. Well, when we multiply like bases, you add their exponents. So you can add 4 plus 4 plus 4, and the repetition of addition of the same number is the same as multiplication. So 4 times 3 is the same thing as 4 plus 4 plus 4. 4 plus 3 is, or 4 times 3 is 12. 5 to the 12. Here we have 2 to the 7th being multiplied by itself 4 times. 1, 2, 3, 4 times. They all have like bases when we're multiplying, so we just add their exponents together. The repeated addition is the same thing as multiplication, so 7 times 4 is the same thing as 7 plus 7 plus 7 plus 7. 2 to the power of 7 times 4 is equal to 28. Alright, let's see if we can do the next one. A to the third to the second power is the same thing as a to the third times a to the third, a to the third, which is the same thing as a to the 3 plus 3. I'm not going to go into the multiplication because then we know a is the same thing as a to the 6th. C to the third to the 4th power is c to the third times c to the third times c to the third times c to the third, which is the same thing as c to the 3 plus 3 plus 3 plus 3, which is the same thing as 3 times 4, which is c to the 12th then. Do you see the shortcut we could have done from the get-go? You simply multiply the power and the exponents together. The power of the power together. Okay, let's see if you can make that algebraic rule based on what we just said. Using the variables a for the base and m for any exponents. We have, if we have any base to a power, and that power is raised to another power, it's the same thing as the base m times n. So that's raising a power to a power. Try these 3 practice questions. See if you can get the answer. You want to push pause and then push play just to check your work. Question number 1. 2 to the power of 3 to the power of 3 is the same thing as 2 to the 3 times 3, which is equal to 2 to the 9th. I'm just going to multiply those two together. 4 to the 6th. 2 to the 10th. Get the idea? This power of the power rule even works for products of, and you know products could be two numbers or a variable and its coefficients. So product rule. Here we have 3y to the fourth power. So you have 3y times 3y times, so 4 times. When you're multiplying coefficients, you would first start multiplying just their coefficients. So the 3 times 3 times 3, it's just another way of rewriting it. So you have 3 to the fourth power, and then you have 4 y's as well, y to the fourth. So 3 to the fourth and y to the fourth. You multiply that power to every exponent on the inside. You don't see where that's coming from. I've got it expanded out, and you can see where it's coming from and expanded out. But 3y, where's its exponents on those 3 and y? Well, the 3 has an exponent of 1, and so does the y to the fourth power. You will multiply that outer power to every exponent on the inside of those parentheses. Try it for the second example. Rewrite it again as 2 to the first, m to the first, to the power of 5. So you can distribute that power as 2 to 1 times 5 times m to the power of 1 times 5, which is the same thing as 2 to the fifth, m to the fifth. So what's our rule going to be used for this one? Now this time you're going to have to use the variable n for your exponent, ab for the two factors of the product. So like this. Any two numbers multiplied together to the power of another number is equal to the first base to the power times the second base to the power. Alright, let's apply this to a few practice questions. Power to a power. 2x to the fourth to the third power is the same thing as 2 to the third times x to the 4 times 3. You would have to multiply to any powers you see there. Or this could be times, because that 2 is a power of 1, exponent of 1, so 2, 1 times 3. Okay, you got the idea. So 1 times 3 is 3, x to the 4 times 3 is 12. Practice question 2. You would write 3 to the third times n to the whatever 2 times 3 is. So 3 to the third n to the sixth. Now later on you will need to, your final answers when they ask you to evaluate the problem or to solve the problem, you will need to simplify the numeric exponents, not the variable exponents, you can't do anything more with those, but simplify the numeric exponents into standard form. So like 8x to the 12th. And 3 to the third, what is it? I think it's 27. N to the sixth. Question 3 is the same format. So we have a negative 1 times 3 is equal to a to the negative third, which is the same thing. Remember, we don't leave our negative exponents, so a to the positive, 1 over a to the positive 3. Last example, 4 to the second power, because that 4 had a 1 of exponent of 1, 1 times 2 is just 2. P to the negative 3 times 2, so that equals 4 to the second. P to the negative 3 times positive 2 equals negative 6. Alright, watch carefully here. The 4 to the second power is positive. we're going to stay on top with that. But the p to the negative 6, that's a negative exponent, so we're just going to bring the p down. Oop. I think I ran out of room. It won't let me draw any further below. Let me erase a little bit. So, oops. Let me erase a little bit so I can write where you can see this. So it's the same thing as 4 to the second power all over p to the sixth power. We moved just the variable that had the negative exponent to our denominator. So 4 to the second, what is that, 16? Over p to the sixth. So that's p to the power of 6. Right, raising a quotient to a power. So quotient, so a division problem or a fraction to any power, you would have to multiply the outer power to every exponent inside of the parentheses, whether it's on the numerator or the denominator. So that it's like saying x to the third is x times x times x. Sorry, y to the third is y times y times y. So how many x's do you have? X to the third, y to the third. So that's what they want to hear, x to the third, y to the third. And our second example is the same thing as 2 to the third over x 2 times 3. So what does that equal to? So 2 to the third over x to the sixth. 2 to the third equals 8 over x to the sixth. So if we were going to write a rule that write a rule that applies whenever we raise a quotient to a power, use the variable n for the exponent and a and b for the numerator and the denominator. So if you have a over b to the power of n, that's saying the same thing as a to the nth over b to the nth. Push play and do the 3 practice questions, or I'm sorry, push pause and do the next 3 practice questions, then push play to check your work. Okay, you ready to check? So, oops. This is saying the same thing as n to the 2 times 4 all over n to the 3 times 4, which is equal to n to the 8th all over n to the 12th. Now, do you notice that we have a division here? So this could be simplified even further. N to the 8th over n to the 2. You know you have to subtract, because whenever you're dividing you subtract. So 12 minus 8 is 4. So what you will do, where are you going to write that 4? Because 12 is bigger than 8, I'm going to just put my 4 on the bottom, whichever number is bigger. So it's the same thing as 1 over n to the 4th. Or you could have thought of it as n to the negative 4, but then you would have to move it to the denominator. So if you just remember to put your answer always where the bigger exponent lies, then you'll be fine. Let's try the next one. So this is saying the same thing as 2 to the, we're actually combining a little bunch of ideas now. 2 to the third, because that exponent to the exponent of the 2. P to the, 3 times 3. All over 2 to the third again, because that 2 had an exponent of 1 times 3. I can write it like that even. Times p to the 2 times 3. So we simplify that further. We have 2 to the third, p to the 9th over 2 to the third, p to the 6th, Look, 2 to the third, 2 to the third is the same thing, so it should cancel out. And you're left with, well, p to the ninth over p to the sixth. When you divide, you subtract their exponents. And the bigger number's on top, so we're going to leave our p on top. 4 minus 6 is 3. So all of that hot mess just turned into p to the third. Question 3. We have x to the third all over 2 to the third times x to the 3 times 3, which is then simplifies to x to the third over 2 to the third x to the ninth. And notice how we have two x's over top of one another. We can subtract, but the bigger number's on bottom, so that's where we're going to leave the 2 to the third. Can stay on bottom. You could actually evaluate the 2 to the third. Let's go ahead and do that. 2 to the third is the same thing as 8. In our variables, 9 minus 3 is 6, but the bigger exponent's on bottom, so that's where we're going to write our x to the 6th. Now, when you have this situation, there's nothing left on the top. We can't just leave nothing on our numerator. You do need to put something there, so let's put a 1 up there. Unlike if you have just a numerator and no denominator, you don't need to put the 1. But if everything is in the denominator, you do have to put the 1. Alright, let's try to apply all of our rules. We'll attempt to use the rule to simplify rather than expanding it out. So which rule do we apply here? I see a exponent to a base to another exponent. So this is a power of a power. What do? We multiply. So n to the ninth. Here we have a power of a product, because we're multiplying. There's the product. So the rule is you take the power to each product. And if they're, you multiply it to the exponent of each product. So r to the 8th. Simplify or evaluate the numeric part of your answer. So 3 to the second is equal to 8. That is a very common one that you will see. 3 to the second power is 8. I would just memorize it. It appears often. Okay, questions 3 and 4. What do we have going on here? It looks like a multiplication. Oops. Multiplication with the same basis. You multiply the coefficients together. Negative 4 times negative 2 equals negative 8. And then we multiply our variables together. X to the second times x to the, what power is that? To the first equals x to the third. Or, third, because you add their exponents together when you multiply. Question number 4 is very similar. You first multiply the coefficients, so the 3, the 1, and the 4. 3 times 1 is 3, times 4 is 12. Then you multiply the variables together. Okay, the 4th, the 3rd, and the 4th, you simply add their exponents. 4 plus 3 is 7, 7, 8, 9, 10, 11. So 12 to the k, 12k to the 11th power. Please, I beg of you that you actually do push pause in between each problem and try to do the problem before I demonstrate or show you the solution. If we were in a class, I'd have you write it on a board and hold it up. So question number 5, we have a 3 over 3. Those are the same numbers. Those cancel out. And then you have r to the second over r to the first. We can use the division property, so it equals r to the 2 minus 1 is 1. And we would leave it on our numerator because the bigger exponent's on the numerator. And you do not need to write exponents of 1, so you can just simplify it by just calling it r. Question 6. Here you have a 3 over a 2. 3 over 2 does not reduce, so our answer is still going to have a 3 in our numerator and a 2 in the denominator. But then we have x to the 4th over x to the 3rd. They're the same basis, so you would have to subtract their exponents. And because there's more x's on top than there are on bottom, we're going to leave the remaining x on top. So 3x over 2. Question 7 and 8. Looks like we're applying the zero property. Remember, anything to the 0 power is always equal to 1. Now, on this question number 8, the only thing that's to the 0 property is that 2b. So that's the 1. We can't do anything else with the 3b to the 4th, so your final answer is 3b to the 4th. So 1 times anything is just itself. Try some more quotient rules, it looks like. You have 2 over a 1. Remember, if a term does not have a coefficient, it's 1. So 2 over 1 can't reduce any further. We're going to just leave that 2 on top. You have x to the 4th over x to the 2nd. With the this rule, you would have to subtract, and your answer would go on the numerator because there's more x's on top than there are on bottom. We don't really need to write that line there because we're not left with anything on our denominator. Oops. Apply your quotient rule again on question 10. 4 over 3 does not reduce, so we still have a 4 over a 3. But our x's can reduce. We have 2 x's on top and 4 on bottom. 4 minus 2 is 2, but there's more x's on bottom than there are on top, so we're going to put our answer on the bottom. Question number 11. We have a 2 over 2, which cancel. 2 divided by 2 is equal to 1. Any number over top of itself is always equal to 1. When we say it cancels out, it just is equal to 1, and we normally don't write 1 as a coefficient or showing multiplication of 1. But when that's the only thing we left over. We do not write 0. This is nothing zeroed out. So you would just finally write 1 as your answer. So 2 divided by 2 is 1. So in the next example here in 12, we have 3 over 1 is 3, but our ends, there's 3 ends and 3 ends, so that means there's no ends left over, so that's what it'll be 3. The x, okay, let me expand this one out so I can show you what the reason why the answer it is. So we have x 2 over 2x. The x's do cancel out because that would be like x to the 1st minus x to minus 1 equals x to the 0. What's x to the 0 equal to? 1. Alright, so that's why we're getting that 1. This one right here would be 3 over 1 is 3 times n to the 0, because 3 minus 3 is 0, which equals 3 times 1, which equals 3. Okay. On number 13, we're using multiplication again. It doesn't matter that the parentheses around the first set of 2a. Oh no, it does matter. I'm sorry, it does matter. So, be careful. This can be a common mistake here. Notice that this 2a is to the second power, but what we're multiplying by is 2 times just the a to the second power. If it was to 2a to the second power, there would be a set of parentheses around that second set of 2a's. So To answer this one, I would expand it out just so you can really see the answer here. 2a times 2a times 2 times a times a. And we can rework one of these. The same thing as 2 times 2 times 2 times 1, 2, 3, 4 a's, or a to the fourth, 2, 3 2's, or 2 to the third. I told you we use often is 8, a to the fourth. There's your final answer. So watch this parentheses. In question 14, here we have a 4 y to the fourth to the negative 3. You would multiply just those two together. So on our numerator we have y to the negative 12th. We will be moving that, but not just yet, over x to the third, negative third, y to the second. Now let's take care of our negatives. Also we have this division of y, so let's take care of that first. Y to the negative 12th minus 2. So watch out on this one. This is y negative 12 minus 2. You see what we're doing there? You can think of it like this. You can think of it as a negative 12 plus a negative 2 because we keep change. Or you can think of it as, oh, same signs. What do we have to do? Add. Even when you change it like this, you'll get the same signs. Add is 14, but the bigger sign wins is negative 14. So we have a y of negative 14. And where do we write it? Well, our answer is going to go where the bigger exponent is. We get a negative 14. But then again, we still don't want to leave it as a negative. So you need to move it to the denominator. So that y to the 14th goes on your denominator. Now don't forget about that x to the negative third. We move it up, change its floor, and make it a positive 3. I am so sorry for yawning. We are just about done, but I've got two very spicy problems for you. And if fractions are not your thing, this is going to be a little tricky here for you. 5 to the 1/2 power to the power of 2. So here we have the power of the power rule. So this is the same thing as 5 to the power of 1/2 times 2. Alright, we need to remember how to multiply fractions to whole numbers. What do? Put a 1 under it. So 5, well, 1 times 2 is 2. You just multiply across. 2 times 1 is 2. Or you could have cross-canceled. Got 1 and 1. So you have 5. 2 over 2 is the same thing as 5 to the first. Any number to the first power is just itself, the 5. Try the next one. This is 4. So before I go any further, do you notice anything about that problem? Maybe you'll notice it here when I do another example. This is the same thing as 4 to the 1/5 times 5, which is equal to, okay, so we need to multiply a fraction to a whole number. Put a 1 under it. The 5's cancel out, 1 over 1. So this same thing as 4 to the first, or just 4. So what's going on here? Do you notice that when you take a number to the fractional power to the power of the same denominator, so the denominator of the fraction and the power right here are the same, and it looks like everything canceled out and you're just left with the base. That base number is your answer. So will that always be the case? Yeah, just as long as the numerator of that fraction is a 1. Because you're multiplying by the reciprocal then every single time. Now you can go to your 2.1, 2.2 guided practice or independent practice. This will need to be submitted in for homework, so if you don't get it done today, please turn it in by the next class.